Here begins the essay. The year 1930, one witnessed the publication of Emil Post's Introduction to a Theory of Nominalistic Functional Calculus, a work of considerable ambition aimed at establishing a novel foundation for mathematical reasoning. This essay undertakes a meticulous evaluation of the claims and arguments presented within that seminal text. Examining its construction from the ground up, we will proceed section by section, dissecting Post's propositions and assessing their inherent validity and lasting impact within the broader context of mathematical logic. The intention is to elucidate the core mechanics of Post's system, acknowledging its strengths and identifying the inevitable points where further development, or indeed, alternative approaches, proved necessary. Section 1. The motivation for a nominalistic calculus. Post initiates his work with a clear articulation of the perceived limitations of existing logical systems, particularly those based on the predicate calculus. His primary concern revolves around the ontological commitments inherent in these systems. Predicate calculus, in its standard formulation, presupposes the existence of objects within a domain of discourse to which predicates can be applied. Post deemed this commitment, however innocuous it might appear to some, to be an unnecessary and potentially misleading metaphysical baggage. He advocates for a more austere approach, one that avoids explicit quantification over objects and instead focuses on the manipulation of symbolic expressions themselves. The motivation, then, can be summarized as a desire to construct a logical framework free from ontological assumptions, a system where meaning arises purely from the structural relationships between symbols. This desire, while seemingly radical, aligns with a broader philosophical trend seeking to ground mathematics in concrete, manipulable entities, thereby avoiding reliance on abstract Platonic realms. The initial claim that predicate calculus necessitates an undesirable ontological commitment represents a significant point of departure from prevailing mathematical philosophies. This essay will investigate the degree to which Post's construction successfully circumvents this supposed commitment and whether the resulting system retains sufficient expressive power. Section 2. The alphabet and formation rules of the calculus. The foundation of Post's nominalistic functional calculus rests upon a carefully defined alphabet and a set of formation rules. The alphabet consists of a finite number of symbols, including propositional variables, which are typically represented by letters, and a set of operational symbols. These operational symbols are crucial as they embody the functional aspect of the calculus, allowing for the construction of more complex expressions from simpler ones. The formation rules dictate precisely how these symbols can be combined to create well-formed formulas. These rules are recursive in nature, specifying the initial atomic formulas and providing procedures for building larger formulas using the operational symbols. Post emphasizes the importance of these formation rules in maintaining the integrity and consistency of the system. A formula is considered well-formed only if it can be derived from the basic symbols according to the specified rules. The claim here is that the restriction to well-formed formulas, rigorously defined by the formation rules, serves as a bulwark against the introduction of meaningless or contradictory expressions. One must meticulously analyze the specific set of formation rules presented by Post to determine whether they are indeed sufficiently restrictive to avoid such pitfalls and whether they simultaneously allow for the expression of a sufficiently rich class of propositions. The limitations or strengths of the calculus will be intricately linked to the particular choices made in defining these foundational elements. Section 3. The nature of functions in Post's system. Central to understanding Post calculus is comprehending his notion of a function. It deviates from the standard set theoretic definition found in conventional mathematics. Instead, functions in Post's system are essentially syntactic operations. They are rules that specify how to transform one or more well-formed formulas into another well-formed formula. These transformations are purely formal, based on the symbolic structure of the formulas involved. One could interpret a function as a sophisticated symbol manipulation algorithm. Post carefully avoids any suggestion that these functions represent mappings between sets or possess any inherent semantic content beyond their operational definition. He emphasizes the purely mechanical nature of these function applications, highlighting the system's commitment to nominalism, where meaning arises solely from the relationships between symbols. The assertion that functions are purely syntactic operations, entirely devoid of semantic content, represents a radical departure from traditional mathematical practice. It becomes pertinent to inquire whether such a purely formal notion of function is adequate for capturing the essence of mathematical reasoning, which often relies on intuitive understandings of meaning and interpretation. This section requires a deep dive into the concrete examples of functions presented by Post to assess their expressive power and their ability to mimic, however indirectly, the behavior of ordinary mathematical functions. Section 4. The introduction of axioms and rules of inference. Post introduces a set of axioms and rules of inference to provide a mechanism for deriving theorems within his calculus. The axioms are a collection of well-formed formulas that are assumed to be true by definition. They serve as the starting points for deductive reasoning. The rules of inference establish how to derive new theorems from existing theorems. These rules are typically stated in the form of schematic formulas, indicating that if certain formulas have been proven, then a related formula can also be considered proven. The combination of axioms and rules of inference provides a formal system for generating a set of theorems, representing the logical consequences of the initial axioms. Post emphasizes the importance of choosing axioms and rules of inference that are both consistent and complete. Consistency ensures that the system does not derive contradictory theorems, while completeness guarantees that all true statements within the system can be proven. The claim that a specific selection of axioms and rules of inference achieves both consistency and completeness is a powerful one, necessitating rigorous proof. This part of the analysis must carefully scrutinize Post's choice of axioms and rules, examining whether they are sufficient to capture the intended logical principles and whether they avoid the risk of introducing inconsistencies. Furthermore, assessing the system's completeness requires demonstrating that any well-formed formula that is true in some appropriate sense can indeed be derived as a formal theorem. Section 5. The concept of deducibility and proof. Within Post's framework, deducibility emerges as a central concept. A formula is deemed deducible from a set of axioms if there exists a finite sequence of well-formed formulas, each of which is either an axiom or follows from previous formulas in sequence, by applying one of the rules of inference, such that the final formula in the sequence is the formula in question. This sequence constitutes a formal proof of the formula. The length and complexity of a proof can vary significantly, depending on the formula being proven and the specific axioms and rules of inference used. Post highlight the objective and mechanical nature of deducibility. Given a set of axioms and rules, determining whether a formula is deducible becomes a matter of systematically searching for a proof sequence. While the search process may be computationally intensive, it is, in principle, a purely algorithmic task. The claim that deducibility is a purely mechanical process, amenable to algorithmic verification, underscores the formalistic nature of Post's approach. This claim carries significant implications for the automation of logical reasoning. It raises the question of whether it is possible to design algorithms that can efficiently find proofs within Post's system, or whether the search space is inherently too large for practical implementation. The efficiency of proof search is a critical factor determining the practical utility of the calculus. Section 6. Analysis of specific examples of theorems. To thoroughly evaluate the efficacy of Post's calculus, one must examine specific examples of theorems that can be derived within the system. These examples provide concrete illustrations of how the axioms and rules of inference interact to generate logical consequences. By analyzing the proofs of these theorems, one can gain a deeper understanding of the system's expressive power and its ability to capture various aspects of mathematical reasoning. Post likely presents a selection of theorems intended to demonstrate the system's capacity to handle familiar logical principles. The choice of these examples is crucial, as it provides evidence for the system's adequacy. Examining the proofs of these theorems might reveal both the strengths and weaknesses of the system. One may discover that certain theorems, which are considered straightforward in conventional logic, require surprisingly complex or convoluted proofs within Post's calculus, suggesting potential limitations in its expressive power or its ease of use. Conversely, one may find that the system offers particularly elegant or insightful proofs of certain theorems, showcasing its unique advantages. A comparative analysis of proofs within Post's system and proofs within alternative logical frameworks is essential for a comprehensive assessment of its merits. Section 7. The system's expressiveness and limitations. A critical evaluation of Post's nominalistic functional calculus necessitates a thorough assessment of its expressiveness, the range of concepts and relationships that can be adequately represented within the system. While Post aimed to construct a system powerful enough to capture the essence of mathematical reasoning, the inherent limitations of a purely formal approach must be recognized. It is possible that certain concepts, which are easily expressed in set theoretic or predicator-based systems, prove difficult or impossible to formulate within Post's framework. The absence of explicit quantification over objects may restrict the system's ability to express certain types of general statements. In addition to limitations in expressiveness, Post's calculus may also face limitations in its deductive power. There may be true statements within the system that cannot be proven from the given axioms and rules of inference. Such incompleteness would significantly undermine the system's potential as a foundation for mathematics. The claim that Post's system is both sufficiently expressive and sufficiently complete to serve as a foundation for mathematics represents a substantial claim requiring rigorous justification. This section must delve into the potential limitations of the system, considering whether these limitations are inherent to the nominalistic approach or whether they could be overcome through further refinements or extensions of the calc. Section 8. Comparison with predicate calculus. A crucial aspect of evaluating Post's system involves a direct comparison with the predicate calculus, the dominant logical framework in mathematics. Post specifically aimed to provide an alternative to predicate calculus. Motivated by his concerns regarding its ontological commitments, it becomes essential to determine whether Post's calculus successfully achieves its goal of avoiding these commitments and whether it offers any advantages over predicate calculus in terms of clarity, simplicity, or ease of use. The predicate calculus provides powerful tools for expressing complex mathematical concepts, including quantification over objects, relations, and functions. It has been extensively studied and applied in diverse areas of mathematics. Post's system, in contrast, represents a relatively less explored approach, with a different set of strengths and weaknesses. A comparative analysis should consider the relative ease with which various mathematical concepts can be expressed in each system, the complexity of proofs, and the potential for automation. This investigation ought to assess whether Post's calculus offers any unique insights or advantages that justify its departure from the established framework of predicate calculus. The ultimate value of Post's work hinges on its ability to provide a viable and compelling alternative to the dominant logical paradigm. Section 9. The role of interpretation and semantics. While Post explicitly aimed to construct a purely formal system, devoid of inherent semantic content, the role of interpretation and semantics cannot be entirely ignored. Even in a nominalistic calculus, it is necessary to provide some interpretation of the symbols and formulas in order to understand their intended meaning and their relationship to mathematical concepts. One might argue that the choice of axioms and rules of inference is implicitly guided by semantic considerations, even if these considerations are not explicitly acknowledged. Furthermore, the application of Post's calculus in specific mathematical contexts inevitably involves some degree of interpretation. The formulas of the calculus must be related to the objects and concepts of the domain being studied. The claim that Post's calculus is entirely independent of interpretation and semantics may be an overstatement. It is possible that the system's effectiveness relies, at least in part, on the ability to provide meaningful interpretations of its symbols and formulas. This section necessitates an exploration of the relationship between syntax and semantics in Post's system, considering the extent to which interpretation plays a role in its development and application. Section 10. Subsequent developments and influence. Following its publication in 1931, Post's introduction to a theory of nominalistic functional calculus garnered attention from logicians and mathematicians, stimulating subsequent research and development in the field of Fall systems. While Post's specific calculus may not have achieved widespread adoption as a primary foundation for mathematics, the ideas and techniques introduced in his work have had a lasting influence. His emphasis on formalization, symbol manipulation, and the algorithmic nature of deduction has resonated with researchers in areas such as automated theorem proving and computer science. Subsequent developments in logic have built upon Post's work, exploring alternative formal systems, developing more powerful proof techniques, and investigating the relationship between syntax and semantics. Post's work serves as a reminder of the diversity of approaches that can be taken in the pursuit of a rigorous foundation for mathematics. This exploration mandates a tracing of the intellectual lineage stemming from Post's work, identifying specific instances where his ideas have been adopted, adapted, or challenged. It is important to assess the lasting impact of his nominalistic approach and to determine where it has contributed to the advancement of logical understanding. Section 11. A reflection on nominalism in mathematics. Emil Post's endeavour to construct a nominalistic functional calculus is inextricably linked to the broader philosophical debate surrounding nominalism. In mathematics, nominalism asserts that mathematical objects are merely names or symbols, lacking any independent existence. This view contrasts sharply with Platonism, which posits the existence of abstract mathematical entities that are independent of human thought or language. Post's calculus represents an attempt to ground mathematics in concrete, manipulable entities, thereby avoiding reliance on Platonistic assumptions. The success or failure of Post's project sheds light on the viability of nominalism as a philosophical foundation for mathematics. A comprehensive evaluation requires examining the strengths and weaknesses of nominalism, considering its implications for mathematical ontology, epistemology, and practice. It is crucial to assess whether nominalism adequately captures the essence of mathematical truth and whether it provides a satisfactory account of the objectivity and universality of mathematical knowledge. The viability of nominalism in mathematics continues to be a subject of ongoing debate, and Post's work serves as a valuable contribution to this discourse. The philosophical underpinnings of the calculus deserve scrutiny, delving into the implications of adopting a nominalistic perspective on the nature of mathematical objects and the meaning of mathematical statements. Section 12. Revisions and criticisms considered against initial claims, contemporary reactions and subsequent criticism directed towards Post's work offer valuable insights into its strengths and weaknesses. Examining revisions to the original system proposed by Post himself or other researchers can illuminate areas where the initial framework proved deficient or required refinement. Critiques may have focused on issues such as the system's expressiveness, its deductive power, its ease of use, or its philosophical foundations. Analyzing these criticisms allows for a more balanced and nuanced assessment of the work's merits. It is particularly important to consider how these criticisms relate to the initial claims made by Post regarding the system's advantages and its ability to provide a viable alternative to predicate calculus. Do the criticisms undermine these claims, or do they simply highlight areas where further development is needed? Addressing these counter-arguments contributes to a more comprehensive understanding of Post's contribution and its lasting significance. Scrutinizing revisions, modifications, and extensions of Post's calculus provides a clearer picture of the system's adaptability and its potential for improvement. These subsequent developments can reveal areas where the original framework proved successful and areas where it required further refinement. Section 13. The enduring significance of Post's work. Despite the potential limitations and criticisms discussed, Emil Post's introduction to a theory of nominalistic functional calculus remains a significant contribution to the history of logic and the philosophy of mathematics. The work represents a bold attempt to construct a purely formal system for mathematical reasoning, free from ontological assumptions. Post's emphasis on symbol manipulation, formalization, and the algorithmic nature of deduction has had a lasting impact on the field, influencing subsequent research in automated theorem proving, computer science, and other areas. Even if Post's specific calculus has not achieved widespread adoption as a primary foundation for mathematics, the ideas and techniques introduced in his work continue to inspire and inform contemporary research. His work serves as a reminder of the diversity of approaches that can be taken in the pursuit of a rigorous foundation for mathematics and the importance of questioning established paradigms. Post's legacy lies not only in the specific details of his calculus, but also in the broader philosophical and methodological principles that guided his work. In conclusion, Emil Post's introduction to a theory of nominalistic functional calculus presents a compelling yet ultimately challenging vision for the foundations of mathematics. While Post's ambitious goal of constructing a purely nominalistic calculus may not have been fully realized, his work has undeniably left an indelible mark on the field. The act of meticulously examining the claims of this work, system section by section, has revealed both its innovative strengths and its inherent limitations. Post's work continues to serve as a stimulating intellectual exercise, prompting further reflection on the nature of mathematical truth, the role of formalization, and the relationship between syntax and semantics. It stands as a testament to the power of human ingenuity in the pursuit of rigorous foundations for mathematical knowledge.